Today, we're going to talk about something you feel every single day, but maybe don't think about too much. It's this invisible force. It governs everything from your morning coffee to the stars in the sky. We're talking about heat and the super clever ways it travels from one place to another. I mean, have you ever really stopped to think about it? Why does that perfect hot cup of coffee eventually turn cold? Or, why does an ice cube you left out just melt into a puddle? It seems obvious, right? But the answer gets down to a really simple, really fundamental rule about how energy works. Okay, so to get our heads around all this, we've got to start with the number one most important rule of heat, the big one. And here it is. This is the whole game, right here. Heat always flows from a hot body to a cold body. Always. It's a one-way street. It never, ever goes the other way on its own. So your hot coffee is literally giving its heat away to the cooler air in the room. The air isn't giving its cold to the coffee. And honestly, this simple idea, this direction, that is the key to understanding everything we're going to talk about today. So, okay, if heat is always moving from hot to cold, how does it actually, move? Well, turns out there are three main ways it gets the job done, and we're going to break them all down. First up, we'll look at conduction, what I call the domino effect. Then we'll get into convection, which is all about riding the current. After that, it's radiation, or invisible waves. And to wrap it all up, we'll see how this all plays into the actual science of cooling. All right, let's dive in. First up is conduction. And the best way to think about it is like a domino effect for heat. So what is it? Conduction is just heat transferring through direct contact. Think solids, mainly. And this is the really important part. The material itself doesn't actually go anywhere. It's just the energy that's passing through it. But how does that actually work, like on a tiny microscopic level? Well, imagine the molecules inside a metal bar are a bunch of tiny little balls, all packed together. Now, when you heat up one end of the bar, that first molecule starts vibrating like crazy. It gets all jittery. And what does it do? It bumps into its neighbor, which makes that one start vibrating, and on and on and on, all the way down the line. It's literally a chain reaction, just this wave of energy passing from one molecule to the next. And here's the cool part. This whole flow isn't just random chaos. It's totally predictable. Scientists can measure the rate of this heat flow, and they even have a name for it, the heat current. The best way to picture it is like measuring how much water is flowing through a pipe every second. It just tells us exactly how fast that energy is on the move. Now get this. This is what I find absolutely fascinating. The math, the physics that describes this heat flow, it's almost identical to the physics that describes electricity flowing through a wire. That's not a coincidence. It shows this really deep, fundamental connection in how different kinds of energy actually work. So let's break that down a bit. You know how in an electrical wire, some materials have higher resistance, right? They make it harder for the electricity to get through. Well, it's the exact same thing with heat. We call it thermal resistance. So, for example, a long, skinny metal rod is going to have more thermal resistance than a short, fat one. Why? Because it's just a harder, longer path for that heat energy to travel down. Okay, so that's conduction in a nutshell. But what happens when the material itself isn't stuck in place? What if it can actually move around? Well, that brings us right to our next method, convection, or as I like to call it, riding the current. Yeah, so unlike conduction, where the energy just passes through something that's sitting still, convection is all about movement. This is what happens in fluids, so we're talking about liquids and gases. And in this case, the heat is literally being carried from point A to point B because the fluid itself is flowing. The classic example, the one we all know, is a pot of boiling water. Think about it. The water at the very bottom gets hot first. What happens when water gets hot? It expands, becomes less dense, and it starts to rise. At the same time, the cooler, denser water from the top sinks down to take its place. Then it gets heated and it rises too. You get this constant circular motion, this convection current. And that's what heats up the entire pot of water so effectively. And you know what? The exact same thing happens with the air in your room. All right, we've covered two. Our third and final way he gets around is, honestly, the most mysterious one of all. It's radiation, which is basically heat transfer through invisible waves. I mean, think about it. This is how the sun heats up the Earth. There's nothing connecting us to the sun, right? No solid, no liquid, no air, just the empty vacuum of space. so the heat has to travel as electromagnetic radiation. To get specific, it's infrared waves. You feel this all the time. When you stand near a campfire, that warmth you feel on your face, that's not the hot air hitting you, that would be convection. And you're obviously not touching the fire, that's conduction. No, that feeling is pure, invisible waves of energy hitting your skin. That's radiation. Okay, now for radiation, there's one super important rule you have to remember. Good absorbers are also good emitters. It's a two-way street. So a black t-shirt, for example, gets really hot in the sun, right? That's because it's great at absorbing all that radiation. But here's the flip side. If you take that same hot black t-shirt and bring it into a cool, dark room, it will also be great at emitting or radiating its heat away, way faster than a white shirt would. So this is all cool science, but how do we actually use this stuff in the real world? Well, look no further than the humble thermos bottle. I mean, it is an absolute masterclass in controlling heat transfer. It's a brilliantly simple design that's made to stop all three methods dead in their tracks. So, how on earth does it work? It's genius, really. First, you've got those shiny silvered surfaces on the inside. That silver coating is a terrible emitter, but a fantastic reflector. It basically acts like a mirror for heat, bouncing all that thermal radiation right back into your hot coffee. Okay, step 2. There's a vacuum between the inner and outer walls. No air. And if there's no air, there's nothing to transfer heat through conduction or convection. Problem solved. And finally, you've got the stopper. It's made of a material that's a really poor conductor, basically plugging the last major escape route for heat to get out. Okay, so all of this, conduction, convection, radiation, it all brings us to one final really important question. How fast do things actually cool down? And the answer comes to us from a very elegant principle courtesy of Sir Isaac Newton himself. And it's beautifully simple. The hotter something is compared to its surroundings, the faster it's going to cool off. That's it. A boiling hot cup of coffee at, say, 90 degrees will lose its heat way faster in a 20-degree room than a lukewarm cup at 40 degrees will. The bigger the temperature difference, the faster the heat escapes. And as the coffee gets cooler and closer to room temperature, the rate of cooling slows right down. And of course, there's some math that describes this relationship perfectly. This formula here, all it's really saying is that the cooling rate, that's the dT over dt part, how fast the temperature is changing, is directly tied to the difference in temperature between the object and everything around it. The bigger that difference, the faster it cools. It's such a simple idea, but it's incredibly powerful. So what does this actually look like over time? Well, this graph here shows it perfectly. Notice it's not a straight line. It's not a steady drop. Instead, the temperature plummets really fast at the beginning, right when the coffee is hottest, and the temperature difference is huge. But then, as it cools, the curve starts to flatten out. That slowdown as it gets closer and closer to room temperature, that's a classic process called exponential decay. Okay, so to leave you with one final thought to chew on, one that kind of ties all this together. We said that good absorbers are good emitters, right? So why do we wear dark clothes in the winter, which are great absorbers? And on the flip side, why do astronauts who have to deal with the insane cold of space wear those super shiny reflective suits? The answer? Well, it pulls together everything we've just talked about, from the sun's radiation all the way down to the heat coming off your very own body. It's definitely something to think about the next time you're waiting for your coffee to cool down.